and welcome to our discussion 3.3. I think I'll try to make this video also just into one. We have a few things to get through, but we'll see if we can get through it in a relatively reasonable amount of time. Honestly, 3.2 and 3.3 I usually do on the same day in class because both of them don't have a lot of theory and they're primarily concerned with some new types of examples and looking at graphs. But there are a few bits of theory we'll actually look at in section 3.3. But first off, we're just going to look at another graph and do some more interpretation. Here we have a function f over here on the right. And we have a lot of different questions. So is f increasing on the interval -8 to -2? Well, f is a function. F was also our replacement for y. So it's asking, is y increasing on this interval, -8 to -2? So this is an interval of x. So -8 to -2 would be between here and here and here on the x-axis. So between -8 and -2, is it increasing? Well, a good way of thinking about it is to think about slope. If you remember when we talked about slope in 2.3, a line had a positive slope if it went up as it went left to right, and a negative slope if it went down as it went left to right. Well, those are basically the same conditions for increasing or decreasing. A function is increasing if it's going up as it goes left to right, and it's decreasing if it's going down as it goes left to right. When we look at between -8 and -2, the function is increasing on that interval because it increased from a y value of -4 to a y value of +6 on -8 to -2. So yes, the answer to that is yes. Is the function decreasing on -8 to -4? That would be from here to here. No, it is not. We just said it was increasing on this whole interval. So on a small part, it wouldn't be decreasing. Is f increasing on -2 to 6? So -2 to +6. It does a lot of things on -2 to 6. You know, it decreases, then it increases, then it decreases again. So the answer to that is no, not in general, but it does do a couple of times. Is f decreasing on the interval 2 to 5? So here's 2 to 5. Yes, it is. It is going down as it goes left to right between x equals 2 and x equals 5. So on what intervals is f increasing? So it's increasing from -8 to -2. Where else? From 0 to 2. And from 5 to 7. Where's it decreasing? It's never constant anywhere in here, so it looks like all the other intervals would basically be where it's decreasing. So -10. Oh, I should actually write the decreasing. -10 to -8. From -2 to 0. From 2 to 5. Those would be all the intervals of increase or decrease. Local maximum. There is actually a definition for this in the book. You might want to look at it. But briefly, a local maximum is a crest that is the highest point in an open interval. So if you look at this point, it's the highest point in the open interval around. So the point is a local maximum, and its value is 6. It's found at -2. So is there a local maximum at 2? Yes, there is. This is the highest point in an open interval around 2. So its highest value is 10. So the local maximum has a local maximum at 2, and the maximum value is 10. Is there a local maximum at 5? There is not. There is a local extrema, but it is a minimum, not a maximum. Extrema is the general term for maximum or minimum. All right, list the numbers at which f has a local maximum. So, local maxes at, well, let's see. We have one here, -2. We have one here, 2. And we have one. Nope, that's it. You might ask, well, what about these two? You cannot have a local maximum at an endpoint because of the condition that it has to be an open interval. If it has a finite endpoint like that, well, that's a closed interval because it has a square bracket. An open interval always has parentheses. So, cannot have it at an endpoint if it's a local maximum. That's different than absolute minimum and absolute maximum, which we'll get to in the next one. What are the values? The values would be the y values. So at -2, it is 6. At 2, it is 10. All right, local min. At, let's see, right here, -8. Where else? Right there, 0. And also at 5. And those values would be -4, 0, and 0. All right, absolute minimum. That is the absolute lowest point in the function. So absolute minimum would be right here. And its value, of course, would be -4. Absolute maximum would be right here at 210. At 2, its maximum value would be 10. Now, it is possible to have absolute minimums or absolute maximums at endpoints. That's a difference from the local ones. Absolute maximum, absolute minimum are just the highest and lowest point, whether that's an endpoint or any other kind of point. Just has to be an actual point, not an empty circle. All right, let's look at these problems. I wanted to look at these because these kind of give you a good idea of the difference between an absolute maximum and a local maximum, and the same thing for minimums. So let's look at 50 here. You see 50, its absolute maximum would be here, 4, 4. Its absolute minimum would be at this endpoint, 5, 0. So absolute minimum at 5, the value is 0. Absolute max at 4, value is 4. It does have a local minimum right here at 1, 1. But it does not have a local maximum other than this one. The local maximum, the only local maximum, is also the absolute maximum of the function. The absolute minimum is one of the endpoints. And then 52 is an interesting case because it has a missing point at 2, 4. It has no point there. That would be a local maximum and also the absolute maximum. But since there's no point there, you approach that value, but you don't actually have that boundary there. So what that means is there is no absolute maximum to that function. There's also no local maximum. There is an absolute minimum, and that is this endpoint. Something like 55 has no absolute maximum, no absolute minimum, also no local maximum or minimum, because they would be at these points, but all of those points are omitted. There is no point at 3, 2. There is no point at -1, -3. 56 is very similar in that respect. Both has no local, no absolute extrema, maximums or minimums. Let's add a little bit of theory in now. Let's talk about even and odd functions. So a function is even if f of negative x equal f of x. The graph of an even function is symmetric in the y-axis. It's a retread of symmetry that we looked at in 2.2. Graphs that are symmetric in the y-axis come from functions that are called even. And here's the algebraic check if you're looking at the actual formula. If f of negative x equal f of x, it's even. And this is true of the graph. And odd, those are graphs that are symmetric with respect to the origin. You can check that from the function by doing this, f of negative x equal negative f of x. So let's actually look at a couple of graphs, and then we'll look at some equations. So for example, 29 here. This is not an even function. It's not symmetric across the y-axis. It is odd, though. You rotate it 180 degrees or flip it both ways. It is. Flip it around the y-axis and the x-axis. It does present the same graph, so it is odd. This is symmetric around the y-axis, so this is an even function. You might ask, what about symmetric across the x-axis? Well, if you think about that, it wouldn't pass the vertical line test in almost every case. You have to create a very specific type of function that if it's the same thing when you flip it across the x-axis, it wouldn't fail the vertical line test. Really, the only thing that pops to mind is the flat line y equals 0, literally the x-axis. Anyway, so yeah, even and odd functions. Let's look at these things. So you might say 38 here. Is that even or odd? Well, go get mine. If I replace x with negative x, so f of negative x, I get 2 times negative x squared minus negative x squared. That will just get me literally this. Negative x fourth, my bad. There we go. Well, because these are both even powers, this will literally get me that. 2x to the fourth. So f of negative x equals f of x. This is even. Odd, I'd have to multiply the whole thing by a negative. If I did that, negative f of x would be negative 2x to the fourth plus x squared. That's not the same thing as the original function, so it is not odd. Or rather, it's not the same thing as this, so it is not odd. You might say, well, that was even because its powers were all even. Is that what you mean by even functions? Well, certainly a polynomial function like this that has only even powers will be even. And a polynomial like this that has only odd powers will be odd. But that isn't the only way to make the even or odd properties work out by any means. It's just an easy check when you're dealing with polynomials. Like this one will be neither, because this is 5x to the 0 and that's x to the 3, so it has both even and odd exponents. If you do h of negative x, you get, let's see, 3 times negative x cubed plus 5, which is negative 3x cubed plus 5, which is not the same as the original function, so it's not even. And if you do negative h of x, you will get negative 3x cubed minus 5, which is not the same thing as this, so it's neither even nor odd. Whereas this one is very similar to a problem we did in 3.1. This is actually an odd function, because if you do h of negative x, you'll get negative x over negative x squared minus 1, which would be negative x over x squared minus 1, because that minus gets squared away. And if you do negative h of x, I'm looking at 46 here, you would get negative x over x squared minus 1, which is literally the same thing as that. So since h of negative x equal negative h of x, this one would be odd. Just a lot of different ways of evaluating the same condition. If you have the graph, I would always work from there. But if you have the equation, you might as well check it from that. I may ask you to do that on the test. Just an FYI. Let's bring out the calculator to talk about some of these problems. You can use the calculator to find minimums and maximums. So these problems ask us to use a graphing utility to graph each function over the indicated interval and approximate any local maximum values or local minimum values. Also talk about where the function is increasing or decreasing. So let's look at 61. Turn it on. Y equals 61. We have negative 0.2 x to the fourth minus 0.6. Don't really need to type in the 0. Oh, I got off, didn't I? I have to go back and change that. X squared. So this should actually be 3. It's negative 0.2 x cubed. There we go. Minus 0.6 x squared plus 4x minus 6. And it wants me to graph in the interval negative 6 to 4. So I'll go in the window and say negative 6 to 4. Let's look at the graph to see what our vertical scale needs to look like. Okay. Looks like I need my vertical scale to be quite a bit further down from there. So I really don't need that much in terms of the maximum. So let's make our maximum a little bit smaller. Let's say 2. Make our minimum, let's say negative 20 and see if that's any better. Yeah, I got to see the minimum there. All right. Well, we can definitely see a minimum and a maximum value. Let's use our calculator to find those values, to approximate them. It won't necessarily give you the exact values if it's an irrational number. It'll give you a rounded off version, but your calculator is still pretty powerful for doing this. So let's go into the calc menu, which is second of trace. We want these two functions. So let's first do the minimum. The way the minimum function works is it asks for, let's zoom out a little bit more than that, just so I'm not covering up my... There we go. All right, I'm going to go back into the calc menu and hit minimum again. I just don't want to obscure what I'm doing with the text. All right, yeah, I can see what I'm doing now. All right, you see my cursor here. I'm going to move that to the left. You see here, it asks a question mark. It's asking for a left bound. That means something to the left of where the minimum is. Well, the minimum is here. So I'm going to go down. I'm going to go past that to the left. And honestly, I just like to have something on the downward slope towards it. So left bound, sure. Right bound, well, I need something to the right of it. So there's something to the right. And then as a guess, you just need to guess something. Just try to be about right on top of it. So it looks like about right there, about negative 3.87. Let's see what it is. Negative 3.76. So, rounded to 2 decimal places, this would be negative 3.77, comma, negative 18.89. Rounded to 2 decimal places, right? So, the absolute minimum would be at negative 3.77. The value of it would be negative 18.89. And if we want to do the maximum, we go back into our calc menu. I believe that calc is actually short for, well, really, it's short for calculate. It might as well be short for calculus, because this is a calculus operation, really, is what we're doing here. So it's the same, really, kind of syntax. it needs a left bound on the maximum. So I'm going to go up here close to my maximum. Then it needs a right bound. Then it needs a guess right on top of it. All right. That is at positive 1.77, negative 1.91. So that's the absolute maximum. Well, it's not the absolute maximum, probably. It's the local maximum. That's what I meant to say. So that's how you find it with the calculator. The last thing we're going to talk about in this section is average rate of change. So this is problem 65 from 3.3. And we're going to find the average rate of change of f of x equals negative 2x squared plus 4 from various x values. So what is the average rate of change? Well, if you think about what negative 2x squared plus 4 looks like, let's look at this graph. So if you plug in 0, you'll get 4, a point there. If you plug in 1, you'll get 2. If you plug in 2, you'll get negative 4. And then let's just do this, all right? Whoa. I'm not super steady with this tablet. But anyway, it's a parabola facing downwards. And if you're talking about average rate of change, well, if, for example, I wanted to talk about the change from this point to this point, well, the change would just be the difference in the y values. So that would be, about 1. But the rate of change is how fast did the y change with respect to the x. So the comparison of the changes. The change in y over the change in x. Well, we've done this kind of thing before. So if I had, say, the rate of change between these 2 points. So that point is 0, 4. And this point is 1, 2. The change in y would be negative 2. It went down 2. The change in x would be positive 1. So the average rate of change between the 2 points would be negative 2. We've done this kind of calculation before, though. You may recognize I subtracted the y values over subtracting the x values. Well, that's what we did when we were calculating slope. And that's indeed what average rate of change is on a function. It is the slope of the secant line, the line connecting 2 points on a curve. So when they ask the average rate of change from 0 to 2, it's really just a slope calculation. You're calculating the y values, f of 2 and f of 0, and subtracting them, and then you're going to be subtracting the x values. So average rate of change is just slope calculation. It's finding the slope of the secant line. So then in this case, this would be 2 squared is 4, negative 2. I think I just did that one, didn't I? Yeah, 2 negative 4. So this is negative 4 minus 4 over 2 minus 0, which is negative 8 over 2, negative 4. Then b, 1 to 3. Well, that would be f of 3 minus f of 1 over 3 minus 1. So that would be, plug in 3, you get 9 times negative 2, that's negative 18 plus 4, so that would be negative 14 minus, plug in 1, that's negative 2 plus 4. Didn't I do that one? Yeah, I did do that one. That's 2. 2 over 2. So that is negative 16 over 2. So that is negative 8. And that's the average rate of change from 1 to 3. And it shouldn't be a big surprise that that's the case. If you plug in 1, you're there. If you plug in 3, you're way down here. So the slope of this line, wow, I cannot draw it straight at all. But the slope of that line is very steep, negative 8. It goes down 8 units for every 1 unit it goes over. And then 1 to 4, that would be f of 4 minus f of 1 over 4 minus 1. I think we've calculated all of those at this point. Well, I guess we haven't done 4. We've done 1. 1 was 2. 4 would be 16 times negative 2. That's negative 32. Plus 4 is negative 28. And that would be 30. So that would be negative 30 over 3. Be negative 10. Average rate of change. And that'll finish us off on this section. If you have questions, please email me or call me. You do have my cell phone on your syllabus in case you haven't looked at it yet. I may end up posting some more videos over the semester. We'll see. It kind of depends on whether we need it or not. The last unit actually has several videos up anyway. They're from an earlier textbook, but they're still pretty relevant. Have a great day.